Welcome to the Real Python Podcast. This is episode 124. Have you wanted to understand recursion and how to use it in Python? Are you familiar with the call stack and how it relates to tracebacks? This week on the show, Al Sweigart talks about his new book, The Recursive Book of Recursion. Recursion is one of those concepts held as a tenet of high-level computer science priesthood. Al explains the fundamentals of writing recursive functions and a critical missing piece in understanding how they operate, the call stack. After completing his research for the book, he concluded that it's a technique that you should understand but rarely use. He also shares the few cases where recursion is an appropriate solution. Along the way, we talk about directed acyclic graphs, solving mazes, exploring file trees, and creating fractal images. All right, let's get started. The Real Python Podcast is a weekly conversation about using Python in the real world. My name is Christopher Bailey, your host. Each week, we feature interviews with experts in the community and discussions about the topics, articles, and courses found at realpython.com. After the podcast, join us and learn real-world Python skills with a community of experts at realpython.com. Hey, Al, welcome back.
Hello.
I feel like I need to invest in some jackets for my 5 Timers Club.
Has it been 5 times on this
not
show?
Yet. No, this is the 4th time.
Oh, wow.
Yeah. So.
Yeah, it's great to be on this show.
Yeah, thanks. I'm excited to have you back, and you've been working on a new book. You kind of hinted at it before, and then I think we talked a little bit about it at PyCon, that you were working on this, that it was coming up close, and so maybe we could set up a show. So I'm excited to have you here and talk about the Recursive Book of Recursion, which should be out by the time this comes out.
Yeah, Amazon has it as coming out on August 16th, but right now you can buy it directly from the publisher No Starch Press at nostarch.com. It's really nice when you pre-order a print book from them, because they'll also give you the PDF and Kindle ebooks for free, without any DRM locking it down. So you can just put it on whatever device that you have.
That is nice. I really like that ability.
Yeah.
To kind of use it in multiple places. So
yeah, owning the content that you buy is quite a nice thing.
How novel.
Yeah.
I guess maybe just a quick thing on it. You had a talk at North Bay Python in 2018 that covers a lot of the initial sort of concepts here. And what it made me think about was, did that talk inspire the book, or was it more of sort of a starting point for you?
It was sort of a starting point, and wow, that was 2018, was it? Because I had the idea for the book, and then I thought, I can just make a little PyCon talk about it. And I originally thought, okay, well, this book on recursion, how much can one write about recursion? This will probably be 100, 150 pages.
Yeah.
I can knock this thing out in 6 months. It'll be fine. And here we are in 4 years later. And okay, it's finally coming out. That's great. It turns out that there's quite a bit that you can write about recursion. And the publisher also thought it'd be great if I just threw in a lot of project ideas. So I have a lot of fractal drawing programs, this Drost image creator.
Yeah, it goes back to a pretty common theme for you in your books, which I think is awesome. Yeah, including projects.
Yeah, to paraphrase JFK, I do these things not because they're easy, but because I thought they would be easy.
Yeah, nice. Yeah, so I think it's very interesting topic, because one of the things that you kind of hint on initially is those of us like myself who didn't go through computer science classes officially, and maybe are trying to catch up on the sly, see these topics and think about them, and kind of want to know, well, how much of that do I need to know as a Python programmer? And I really feel like the book is answering a lot of that. And also kind of the idea that if you're looking for a gig and potentially facing an interview, this is like a common sort of place that you've seen that. Had you ever had that experience of a job interview or they ask you like a recursion kind of question?
I don't think I've personally had that happen to me, but I do know that sort of recursion is one of those topics that do get brought up in job interviews. And in fact, one of the ways that I try to market the book is saying like, well, you'll need to know this for coding interviews. But recursion is one of those things where no programmer will ever actually need to know it, but every programmer should know it, and no programmer should ever actually use it. So it's paradoxes within paradoxes, which is appropriate enough, I guess.
Yeah. Yeah. So do you want to dive in with like kind of like an initial, like the concept? Because I like using this forum of the podcast as a way to kind of feel free to ask any kind of questions. And I think, the first one would be, okay, well, what is recursion?
Okay, so what is recursion? And a lot of people are really intimidated by this topic, but I feel that a lot of people have this intuitive sense of it. And I give a broad definition of a recursive thing is something whose definition includes itself. This is going to be very interesting how I can describe this on a podcast because it's often a very visual
Yeah.
thing. But if you've ever seen the Sierpinski triangle, or if you've ever played the Legend of Zelda games and you have the Triforce, it's a triangle that has an upside down triangle inside of it. And that forms 3 new triangles on the corners. And if you just keep putting upside down triangles inside of those triangles, you'll form Sierpinski triangles in those 3 corners. And then now you have 9 triangles and you can make Sierpinski triangles out of that.
Yeah.
And so this produces a fractal image, and a fractal is a recursive shape. So really you could say that, well, a Sierpinski triangle is a triangle that contains 3 Sierpinski triangles. It's a thing whose definition includes itself. You could also think of sort of that movie Inception, where people are having dreams while they are dreaming, and then while they are dreaming again.
Yeah.
And a lot of people start making recursion jokes that sort of turn into infinite loop jokes more than recursion jokes. And
Yeah.
everybody feels the need to start making recursive jokes anytime the subject is brought up. But for programming, a recursive function is a function that calls itself. And you might want to think like, well, why would I ever do that? And
Yeah.
I agree. Why would you want to do that? And if you try to do that, you'll just get a weird error message, which is actually a Stack Overflow, which is where the website gets its name from.
Yeah, I like your example, that shortest one is I think easily repeatable on a podcast. That you would
Oh yeah,
just do def shortest, and then your brackets colon and then call in the next line inside the function shortest with a pair of parentheses and then try to run that.
Yeah, it's a recursive function. It contains 1 line of code that calls the recursive function, and it does nothing useful except demonstrate what a Stack Overflow is.
Yeah.
But it turns out that there's some useful things that you can do that recursion as a programming technique is really suited for. But also there's lots of things that I feel like a lot of programmers just use recursion to feel smart and make their code very convoluted and hard to understand. And then they just call that elegant code, which I would not agree with that. But to understand recursion, there's a couple concepts that we have to go into that, if you're just a programmer, like making a to-do list and you're starting out and you want to make web apps or something like this, you might skip over these fundamental computer science topics, even though you already understand and use them, but you've never really thought about them specifically. And that's what functions are and what stacks are. So I like to think of functions as mini programs that your program can run. If you think about it, a function has some code.
Yeah.
And whenever your program wants to run that code, you can call that function. So you can make your own functions, or you can call the functions in some software library or some other module that other people have written. And it's really nice to have functions because otherwise, every time you want to run that code, you would have to copy and paste that code over and over again. And if you ever want to make a change to that, to fix some bug or to add a feature, you would have to make that change every place that you copied and pasted that code. And that's just a logistical nightmare.
Yeah.
You might not make changes everywhere you need to. You might have other things. Things can get out of sync pretty fast that way. So functions are great to just have the code in one place. And also functions can call other functions as well. So it's a great way to reuse code that way. But the one thing that I feel that a lot of people sort of, they know this, but they don't know that they know this. And that is that function calls aren't really one-way trips for the program execution. Like if you call a function, the execution doesn't just move to the function, but also when that function returns, it goes back to the line of code that calls it. And when you have like a function A that calls function B, that calls function C, when C returns, it doesn't just go back to the global scope of the program, it returns to function B. And then when function B returns, it returns back to function A. And then function A returns back to the global scope.
So you're really climbing that sort of stack that you're talking about.
Right. Yeah. And a stack is how your programming language interpreter or the code that the compiler adds to your program. A stack is a data structure that's used to keep track of all of these things. And so then I have to go into what stacks are. And if you've ever used a Python list, you've sort of used a stack already. In fact, if you just had, if you have a Python list and you only ever use the append and pop methods to put something at the end of the list or remove something from the end of the list, that's essentially using a list as a stack. And you can only examine the last item in the list. So actually it's a lot more restrictive than a list is. And so you might wonder like, well, why would you want to use that? Why wouldn't you want to just use a list? And that goes down into computer architecture and machine language where the programming constructs are a lot more simpler. And we've just built up, we've used these simple concepts to build up elaborate things like Python lists or Python dictionaries, which are so much easier to use when you're actually making an application, something that actually is useful instead of just a bunch of theoretical computer science stuff.
Right. Yeah. One of the things that I thought about with stacks that your talk shows, and definitely the book gets into, in that I thought was really interesting that you talked about the Stack Overflow. Not to derail you, but I was wondering about something as you ran this program, which was this sort of shortest thing that we were just talking about before, where shortest is calling shortest is calling shortest is calling shortest, and so forth. And then, you get the error at the end of that, and then it'll basically say that this ran 900 and 96 times, and then there's like 4 times above it that it's showing in this traceback of the error.
Yes.
And I didn't really put 2 and 2 together for a while, that's actually when you have an error and it's showing this idea, it's showing the stack, or at least a portion of it, like the most recent calls, if you will, that are in it. And then, in this case, it would actually show that I guess Python has like a limit, right? It's 1,000.
Right. And that's kind of an artificial limit. Just, wow, how much history should I go into?
I don't know if you have to go that far. Yeah.
Well, so, I mean, even functions themselves are constructs that we kind of take for granted. But originally with, if you're just writing code in assembly, you don't necessarily really have functions. You just have what is essentially a GOTO instruction. You just tell the execution, like, okay, when you're done here, if this condition is true, jump to this other address in memory and start running the rest of the program from there. And why this was sort of such a nightmare to debug is that your program would crash at some point and you would have no idea how it got there. There's no traceback because there is no call stack because there are no functions. And so having functions is really nice because then you can at least sort of see like, okay, this function called this function, that called this function, and that led me here. So then you can sort of, trace back
exactly
to what the original problem is. Whereas if you just have GOTO, you have none of that context. It's sort of like you were leaving a trail of breadcrumbs behind you, and then you look back and you realize that, nope, all those breadcrumbs were eaten by a squirrel or something. They're all gone, and you have no idea where you are or how you got there.
Or the person you were following was teleported somewhere else.
Yeah, and so I believe this is the big thing with structured programming was adding functions, and it's so much nicer than just having a bunch of GOTO instructions. everywhere. This would be called spaghetti code because the path that the execution took with all these GOTO statements was just like strung all around over and under itself, and you couldn't really make
Yeah.
heads or tails of it. And so the traceback is really nice. And what you're looking at is essentially information in the call stack of when that error happened, because the traceback will say, oh, a function A called function B called function C, which then ran this line of code that caused the problem. And the call stack is a stack data structure that keeps track of that. And so just to go back a little bit, so a stack is a data structure. You can think of it like a list, except you can put data on the stack one at a time. We call it pushing data onto the top of the stack. And then you can pop data off of the top of the stack to retrieve it later. So it's sort of like a very restricted list, where instead of the end of the list, you have the top of the stack. And we call it a philo data structure because the first value that you push onto the stack will be at the bottom of the stack. So it'll be the last item you take out. So first in, last out.
Okay.
Is how that happens. And this is, a stack is pretty much one of the simplest data structures you can have in programming. It's just a large contiguous area of memory, and you just need to have a pointer at the beginning of the stack and a pointer at the end of the stack. So it doesn't take up a lot of memory either, which is really important for embedded computing, but also just back in the days where 64K was a lot of memory. And so the call stack, which is completely invisible, by the way, you can't look at your source code and see oh, this is where the call stack is adding these function calls to the call stack and things like that, because all of this is handled in the background automatically for you. And it's one of those blessings and curses that it's really convenient to have functions, but it's also hiding away this detail that you might need to know about if something goes wrong and you have to debug a program. And I feel like the main reason recursion is so dreaded and so intimidating to a lot of people is because I feel I sat down and I thought, okay, why is recursion so difficult? People are notoriously fearful of recursion. And I think if you type into Google recursion is, and then you just let Google autocomplete, it'll say recursion is confusing, recursion is bad. I remember is one of them. And because the whole idea is kind of silly, okay, yeah, you have this recursive function that calls itself, and then it calls itself, and it calls itself. Eventually, we're going to run out of the memory allocated for the stack, which then causes a stack overflow. And if you have a compiled program from a language like C, this could cause it to crash. But Python being an interpreted language, it keeps track of this also for you. And so it has this artificial limit built in of 1,000 function calls. And it basically says, hey, if you have a function that calls another function, that calls another function, and this keeps happening, and none of those functions are returning, and that happens 1,000 times, something's gone wrong. I'm going to just shut down the program and give you this nice Python traceback, because otherwise your operating system it'll crash for real, and the operating system will then say system internal corruption, sys stack, blah, 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 and then some hexadecimal numbers or something like that. And with Python, you can even increase this limit if you really need it. I mean, it's easy for us to sit here and say nobody will ever need more than 1,000 function calls without returning as part of their normal program running, and then somebody will do that. And so it's okay, we can increase this. I think on my Windows 10 laptop, I've increased it to about 2,700 before the operating system will start kicking in. I really have caused an actual stack overflow, and the operating system has crashed my Python program instead of the Python interpreter doing that.
So it's just you have a program that's super complex that needs to go on that large of a journey?
Oh, no, it was just the Stack Overflow testing program. Okay. I mean, yeah, all my normal programs, you might have functions calling other functions and so on, but maybe a dozen or so?
Okay.
The thing that causes a Stack Overflow isn't a bunch of function calls, but function calls and you're not returning from the functions.
Yeah. They're all... You're creating this tower that's ready to topple.
Because every time you call a function, you are pushing new data about that function call onto the call stack, and then when the function returns, it's popping that off of it. So it's constantly growing and shrinking the call stack. And usually, 99% of the times when you've caused a stack overflow, it is because of some bug that has resulted in your recursive function calling itself over and over again out of control.
Yeah. Hence why you're saying that not only is it kind of hard to understand sort of just looking at the code, but it's easy for you to write yourself into that situation.
Yeah. And it's, a lot of programmers kind of get a kick out of, once they understand this kind of complicated topic, they just want to use it everywhere. And it makes you feel really smart to have this recursive algorithm working. And so another part of when I was writing this book, because I looked around and I saw like, well, there's all these bad recursion tutorials and they all seem to be just copying each other. And I really thought like, what makes recursion hard to understand? And I said, oh, okay, people never really talk about the call stack and they just, it's all implied. And so, that's confusing. There's a whole critical section of this concept that isn't even being addressed or pointed out. So that's confusing. And then I also thought like, well, what is recursion actually good for?
Yeah, that's what I was wondering about too.
Yeah, there's two examples that I feel like every recursion tutorial uses over and over again, and it's factorial and Fibonacci. Factorial is when you basically have a series of multiplications, 5 exclamation mark, which that's how you write it out. It would be 5 factorial. That is equivalent to 5 times 4 times 3 times 2 times 1. So, this is used in mathematics. It's not very common in just, day-to-day arithmetic. Hopefully you're not using this to calculate your taxes because factorial numbers get pretty big pretty fast.
Yeah, exactly.
But, if you think about it, there is sort of a recursive nature here because I'll use a much smaller example. So 3 factorial is 3 times 2 times 1, and 2 factorial is 2 times 1. So really, you could think about it as, okay, well, 3 factorial is just 3 times 2 factorial,
right?
Which is 2 times 1. And if you just generalize this, the factorial of any number n is just that number n multiplied by factorial of n minus 1. Again, it's sort of like, oh, okay, well, now you have this recursive definition. If you wrote a factorial function, it would call the factorial function just with n minus 1. Now, you can't have this call itself forever, of course. And so then eventually it gets down to 1, and the factorial of 1 is simply 1. And this is what we call the base case. It's the set of circumstances where your recursive function stops making recursive function calls to itself. And the other cases are called recursive cases, and that's when the function does call itself. And this is another thing that I feel like is not pointed out, even though it is kind of obvious when you say it out loud. Every recursive function needs to have at least one base case, because otherwise it'll keep calling itself and never stop, and then it'll cause a stack overflow.
Yep.
And it also needs to have at least one recursive case. Otherwise, it never actually calls itself, and it's not a recursive function.
Right, okay.
And so, if you have to write a recursive function, thinking about, okay, what is the base case, what is the recursive case, is often a really good starting point. Now, the big problem with factorial as a recursive function is, well, what if you want to get the factorial of 1001? Python only lets you do 1000 recursive function calls before it causes a stack overflow. So if you have, the factorial of 1001 is 1001 times the factorial of 1000, and then that has to make a recursive function call. You're going to have, 1001 recursive function calls, and that's going to cause a stack overflow. Even though, if you just put this in a loop and calculate the factorial the iterative way, which iterative meaning you're just using a loop, Python can handle that easily. It takes, a millisecond to run that calculation. But with recursion, it's going to crash the program. And I feel like that's very telling about recursion as a programming technique, where it seems like it has this mathematical elegance because you're defining factorial in terms of itself.
Which seems really elegant and fancy, yeah.
Yeah, but in reality, it's completely impractical and will actually just crash your program. And because this is a case where, this is a legitimate case where you really would want to have a function that just does make more than 1,000 function calls without returning. It's just calculating a very large factorial, but you don't want it to cause a stack overflow. And there's a whole other technique called tail call optimization, which is also called tail recursion or tail call elimination. It has several different names. And that's like sort of a hack that gets around this stack overflow part as well. But, at that point, you're patching together all of these additional concepts to make up for your already complicated concept. And I think you know what, if you took any beginner programmer, I was like, hey, write some code that calculates the factorial of a number, they would just say, okay, they assign a variable to 1, and then they put a for loop, and then they just multiply that variable by increasing numbers, and then you have it. It's really simple. But recursion has a way of making simple things complicated.
Yeah, totally.
And so the other thing is the Fibonacci sequence. This is where you have a sequence of numbers that begins with 1 and 1, or sometimes 0 and 1. And the next number in the sequence is the sum of the previous two numbers. So if you started off with 1 and 1, well, the next number would be 1 plus 1, so 2. And then, so now your sequence is 1, 1, 2. And the next number would be, well, the last two is just 1 and 2, and that would be 3. And then the last two then is 2 and 3, so the next number is 5. And then the next number is 3 plus 5, and that's 8. This is one of those things where it's a mathematical concept that's easy to grasp, and it also is used in a lot of illustrations. And there's something about sunflower seed arrangements, or pine cones have an arrangement that follows the Fibonacci sequence, and other things like that. And so, but if you think about the Fibonacci sequence, if you wanted to write a loop, again, doing this with a loop is really simple, but we could make it even more complicated with recursion. If you want to find the nth Fibonacci number, that's just the sum of the nth minus 1 Fibonacci number plus the nth minus 2 Fibonacci number. So, the 10th Fibonacci number is just the sum of the 9th and 8th Fibonacci number. But this causes another problem if you start thinking about it, so that every call to the Fibonacci function that you've made results in 2 more calls to the Fibonacci function. And those 2 calls then result in 4 calls to the Fibonacci function. And those 4 calls result in 8 more calls. And you have this exponentially growing or geometrically growing number of function calls. Yeah, a loop to find the 50th Fibonacci number, that'll run in, half a millisecond. But recursive Fibonacci function, if you tried to find the 50th Fibonacci number, that would take longer than the universe has existed to finish that calculation.
Wow, yeah.
And there's also another workaround this, because, if you think about you're calculating the 10th Fibonacci number, then you have to call Fibonacci on 9 and 8. But when you call Fibonacci on 9, you're getting the 8 and 7 Fibonacci numbers. But wait a second, you've already calculated the 8th Fibonacci number, so there's no reason to redo that calculation. And so you can then create a cache of all of these results. And this is another thing that's often used in dynamic programming. It's called memoization, not memorization, but memoization, like writing a memo.
It's even more short term, huh?
Yeah. It's a very fancy word for, hey, when you call this function with this argument, remember what that function returns. And so the next time that you call it, just don't bother doing the calculation, just return the result. And so you're taking up computer memory to save yourself on execution time. So it's a trade-off between memory and CPU power right there. But again, this is we're coming up with these hacks to solve something is this actually useful? And it's really telling that Fibonacci and factorial are you'll find these as the examples in every single recursion tutorial. They're the first things that get thrown at you. Also, you would never want to actually use them in real world code because they just don't work.
Well, yeah, they fall apart after, when you get into the the 20s or something like that.
Pretty
the
quickly,
numbers.
yeah. It's sort of like I have invented this new computer. It just can't handle any numbers larger than 12. It's like,
There's hard times with
well,
those ones, yeah.
yeah. If you have to add single digit numbers, though, it is so fast and great. Let me tell you.
Too funny.
This kind of gives recursion this reputation as like you have to be a super genius to understand it and wield it properly, and really I find it kind of tedious more than anything, and not that useful. And I thought I'm going to write an entire book where I just point out how kind of awful recursion is. But
that's what I kind of thought about. This is sort of this the previous book you had done. We've talked about several books, but the one I was thinking of is kind of beyond the basics.
Yeah, beyond the basic stuff with Python.
Yeah, how that one was kind of a bit of an advice book in the sense that you were saying, hey, if you're going to approach Python, maybe you're kind of at this intermediate level. Here's some advice. Here's some ways that you can approach things to kind of think of stuff. And this is sort of a bit of an anti-advice, or at least a bit of a cautionary tale of like, yes, this is important that you understand what this is because people talk about it all the time. But
right.
But yeah, there's all this sort of like potential messy baggage tied in with it. And then
programming,
but you do have some good advice too, like the actual uses that are really good for recursion.
Yeah, the programming world is full of people giving half-remembered bits of bad advice to other people and passing that off as knowledge. And remember, these are also, in a way, my opinion as well. I'm sure there's a lot of functional programmers who are just, they're already writing up their strongly worded DMs to me right now because I'm sort of bashing recursion. But yeah, recursion isn't all bad. It's just that I feel like it's overused in places where it doesn't need to be used. Because here's another thing that, and a lot of this stuff I had to figure out while I was writing this book. It wasn't necessarily things that my computer science professors pointed out to me, but there is literally absolutely nothing that a recursive algorithm can do that you can't do with a loop and a stack. Because essentially what your recursive function is doing, it's using the call stack as a stack, as its stack data structure, and it's running the function over and over again. So it's sort of using the code in the function as a loop. But really every single thing that you can write as a recursive function, you can write iteratively, just using a loop and a stack. And there are some recursive functions where you don't even need the stack. And I can go into tail call optimization and tail recursion later. But I feel like if you have a recursive function that doesn't even need a stack, this is a sign that you shouldn't be writing this recursively. You're just making this harder on yourself. But I do want to go into the things that recursion is useful for. And I thought about it a lot, and I wanted to get it down to something really simple. And I thought, okay, recursion is actually a pretty neat technique to use whenever your problem involves a tree-like structure and backtracking. So I can use like a maze solving algorithm as an example. If you think of a maze as just a series of intersections where you, and there are some restrictions on, like, the maze can't have any loops in it, some other like minor restrictions. But for most mazes, a maze is really just you come to an intersection where there's two or more different paths that you can take, and you just go down the first path, and then you'll come to another intersection, and you'll then have to pick a path there. And eventually, so that's essentially your recursive case right there. Your recursive function is saying, hey, I'm at an intersection. Let's try each of these paths. And whenever you try a path, it just leads to another intersection. So your recursive function would be calling itself there. And then the base case is when you eventually get to a dead end. So, hey, when you get to a dead end, just backtrack earlier to an intersection and then try another path from that intersection. And then if you continue doing this over and over again, what you'll find is that either you've tried all the paths from an intersection, in which case you should backtrack another level back to a previous intersection, or you'll eventually find the exit. And if there is no exit, you'll find that you have backtracked all the way back to the starting point and you've fully explored this. And if you can think of it as as a diagram where you have the intersections as a node, and then there's just lines coming from each of these nodes to other intersections, and then those intersections branch out into other nodes, and then a dead end would just be a node with no branching paths from that. It sort of forms a tree-like diagram, and so this is the tree-like structure right here. So I feel like a recursive way of solving this is actually pretty nice, because solving this with a loop and a stack, that's definitely possible, but it kind of gets a little bit confusing. I feel like the code would be a lot easier this way. It is useful for some applications. So I listened to the functional programming episode with Bruce Eckel on the Real Python podcast.
Oh, cool.
Yeah, and
nice.
Yeah, he talks a lot about that. I feel like I also never really got functional programming, but now, learning about recursion, I can see like, oh, that's what they're sort of talking about. I'm still not into functional programming, and I can see why languages like Haskell still haven't taken off in popularity. I mean, for me, I first learned about Haskell, I think, in like the early 2000s, and every 4 or 5 years I'll check in on it again, just to be like, hey, are people actually using this language yet? No? Okay, I'll check on you in 5 years then. And that just doesn't happen. But there are a lot of functional programming concepts that you can do in Python that are really handy. And I cover some of those in the book as well. There's chapter 7, I guess, is I go into memoization and dynamic programming. Mostly this book is just like a bunch of the classic recursion examples.
Yeah. I was thinking about one of those as you're talking about that sort of maze solving one. You have an example in there, which I didn't get to dive too deep into, but it was the idea of sort of filling a space, like the fill algorithm that like a paint program would have. And what I think of that is like, okay, that's kind of like a maze that has no exit. You're basically trying every block.
Right. The point is you just want to see every single hallway in the maze.
Yeah.
The quote unquote maze there. So flood fill is another thing where the recursive code is actually, I feel like, easier to understand, but because images, you can have 10 megapixel images or something like that, you will likely cause a Stack Overflow if you try a recursive flood fill algorithm. This is in a lot of like MS Paint or Photoshop. This is the tool where you can like click on an area and it'll just fill in that area with color. That's the flood fill algorithm, and it turns out that's you don't strictly need a stack data structure. You can really have any data structure, so it doesn't necessarily have to be solved with recursion. You could have a Python set, for example, to do that. But yeah, there's a lot of places, and this is why I say, like, recursion is something that you will never need it, but everybody should know it because it does actually pop up in places. So I guess everybody should actually know it.
Yeah.
But also it just gets overused, and so I think it gets a bad reputation there. And the other part that recursion comes into, and I don't go into this in the book because it's such a big topic on its own, but it going into parsers and compilers.
Mm-hmm.
If you wanted to create your own programming language, this is sort of the starting point of that. So you could think of like a Python expression like 2 + 2. And so that's just a bunch of values and the plus operator. And that evaluates down to a single value 4, the integer value 4. But, an expression itself can contain other expressions. You could have 2 plus and then the parentheses, even this I don't know, 3 times 5 or whatever like that. And so these expressions contain other expressions. And so the way the computer science works out, when you have programming languages, there's a concept called like the grammar of a programming language, and it forms an abstract syntax tree. And you hear about all these concepts, and it's really nice to learn about recursion because suddenly you realize like, oh, hey, I've dealt with this before. And I feel like that's one of the great things about having a formal computer science education is that you don't strictly need a CS degree to write programs that are very useful. But there have been times where I sort of realize, like, actually, I wonder if I'm putting way more effort than required. And if I just knew some of these underlying theoretical concepts, it would make my life much, much easier. And I feel like, yeah, a lot of people are sort of intimidated by computer science as a topic, and mostly it's just tedious. It is sort of tricky. I don't want to take away from that, but mostly it's just like a lot of different little things to learn. But as you build up all these concepts, you can add them together, and then you find yourself just much more effective as a software developer because of it.
This week, I want to shine a spotlight on another Real Python video course. It touches on a topic we're discussing this week, recursion and memoization. The course is titled Caching in Python with LRU Cache, and it's based on a Real Python tutorial by Santiago Valderrama. And in the course, frequent co-host Christopher Trudeau is your instructor, and he shows you what caching strategies are available and how to implement them using Python decorators, what the LRU strategy is and how it works, how to improve performance by caching with the LRU cache decorator, and how to expand its functionality and make it expire after a specific time. I think it's a worthy investment of your time to learn about the performance advantages you can achieve with the LRU cache decorator. Like most of the video courses on Real Python, the course is broken into easily consumable sections. And you get code examples for the techniques shown. And all course lessons have a transcript, including closed captions. Check out the video course. You can find a link in the show notes, or you can find it using the search tool on realpython.com. Yeah, one of the things that kind of came up through me looking through your book, and it brought up kind of conversations I've had in the past where I didn't per se stop the person and try to get a better understanding of the thing, was this concept of the tree structures that you're talking about, following, not if it be a maze or a file system, and walking through, and that definitely made a lot of sense to me. And then it kind of led to this thing called a acyclic graph, or a directed acyclic graph, or DAG.
Yeah.
And I hear a lot of people talk about graph theory and all this kind of like other sort of like higher level stuff, and it just felt like, again, a moment for the monks to like,
Right.
you may pass into the CS halls now, because you understand this thing. And I'm like, oh, actually this is okay. It's just trees, and understanding that trees kind of are sort of a one-way thing. That's the idea that you get to the end and you have to backtrack. But I was like, okay, this is starting to kind of tie a lot of those things together, which I really liked about the book. It was really helping me with a lot of those things.
Right. I try to have a focus on practical examples, or at least running code. And that's the other thing about this book, is that it's actually not a Python book.
Yeah.
It's sort of it's a general programming and computer science book, and I have all the code examples in both Python and JavaScript. Like, it's very important for me that I have runnable code as the examples in all of this, because I feel like if you just talk about these abstract classes or abstract concepts, the priest class of computer scientists rarely seem to find it necessary to explain, like, oh, an example of this, of a directed acyclic graph is think of a maze and solving a maze, and you can show how any maze is actually really just this graph structure, and we have recursive functions that can work on these graph structures, and so therefore you can write a recursive algorithm to solve mazes. And once you put it into terms that people can see and play around with, it becomes that much more understandable. In a lot of these, I've started doing this in my books and tutorials. I've started using playing cards as a prop for explaining these things. And I wish a lot more instructors and computer science professors would do this, because playing cards are cheap and they're familiar, and they're these things that you can hold them in your hand and move them around a table surface, and they have numbers on them, so they're in order, and there's multiple suits.
They're unique, yeah.
Yeah, and so for sorting algorithms, I feel like everybody should always just use playing cards as a way of running the algorithm with playing cards in their hand, because otherwise it's a bunch of abstract concepts and you don't necessarily know it. But also just for drawing out diagrams, like a stack data structure is like a stack of playing cards, and in the stack you can only access the data at the very top of the stack, which is, oh, you can only see the card on the top of the stack of playing cards, and you can also see you can add new cards to the top of stack, and you can take cards off the top of the stack. And oh yeah, playing cards this is like a practical tip to any instructor out there, or just if you're learning how to code on your own. Playing cards are an excellent prop, I've found.
Yeah, totally. It makes me think about this guy who creates some amazing sets of games. This guy, Zach Gage, he's kind of known for making some different, solitaire games like Flip Flop Solitaire, but he just came out with like a new game called Knot Words, like tied in a knot, KNOT.
Oh, okay.
It's a fun little, kind of iPhone game in the sort of Wordle era of games. But he talked on a podcast, heard him, speaking about that he would never go to like immediately start programming something. He would, break out a deck of cards or get physical things on a tabletop and try this out in like a physical space. And I feel like you do that a lot too, because like a lot of your examples are, a little simpler. You can maybe hold them in your head as you're kind of programming them in, and I really appreciate that. And this, they're definitely the examples in this book are included in that you can kind of see them, and then you are also early in the book showing the stacks and kind of like that visualization helped me kind of grasp the idea again kind of quickly. And I immediately thought to myself, was like, well, what if it wasn't holding all those in memory, and that kind of led me to the idea of this whole tail call thing. And then, eventually learning that that's not something that's, appropriate in Python, that they decided that we're not going to do that. And so it was just, I don't know, I felt like I was being led through it, even though I haven't quite gotten through the entire book. It's been really useful that way.
Yeah, and it's just that computer science is so abstract.
Yeah.
I mean, it's practical because we use computers all the time, but it's also has that sort of mathematical abstractness. And it's, once you understand it, then of course it's easy. And I feel like this is why recursion, or just programming in general, is so hard to teach, is because, once you understand it, you're like, oh, okay. And then you want to just sort of introduce other people to all these huge concepts that just fly over their head. There is
right.
There is I can enter into the controversial opinion section of the podcast episode right now, and
more DMs
possibly
coming.
Make yeah. So there is a book called The Little Schemer that I believe came out in the 1980s, written by a couple of MIT professors, and this book teaches Scheme, this functional programming language, and it starts with recursion. You don't even really use loops in it, and there's like 5% of the population that really loves manipulating abstract symbols according to arbitrary logical rules for the sake of manipulating abstract symbols according to arbitrary logical rules. It's just like a fun thing, and my brain is kind of like that. But for the rest of society, people are just going to look at that and just be kind of confused, and I feel like a lot of people who really love this book, they kind of get it. And then they're like, oh, wow, this book is so amazing. It's great. It really it teaches you how to think and points out all these ideas. But then the vast majority of people kind of read this, and I really worry that they're going to say, well, I don't get it. I guess I'm just too dumb to program. And then they sort of just give up on it. And so I wanted this book to sort of be the counter to that of, no, there's just all these tiny little concepts, and I want to give demonstrations and examples of all of these step by step, and have actual, not just descriptions of algorithms, but actual runnable code.
Yeah.
You can type it in, you can run it under a debugger one line at a time and really see how that works. So The Little Schemer is a book that is very much beloved by a lot of computer scientists or the sorts of people who like work at Google because they have PhDs in whatever, and they're just really used to dealing with abstract concepts. But I gave it a 1-star review on Amazon. I was just so like, after a while, I got through about 3/4 of it. And I just thought like, oh, this book really needed an editor. And it's mostly, I'm just concerned that a lot of people read this book and it has these cute drawings of cartoon elephants on it. And it's like, oh, this book seems like it should be for kids or something really easy. It has cute little elephants in it, but I don't understand it at all. And I worry that it's the sort of book that a computer science professor thinks is a great book for beginners rather than a book that beginners think is a good book for beginners.
Yeah.
My other controversial opinion on recursion, I think that tail recursion should never be used. Like recursion, I say like, oh, it's often overused, but recursion has its uses and it's great for some things. I think tail recursion should never be used. If you're finding yourself using tail recursion, you've made a mistake, and you should stop using recursion and just use a loop instead. And this is something that I came upon on my own, and I never realized how deficient my education on recursion from my computer science degree really was, because they talk about, oh, here's tail call optimization or tail recursion as it's called. And so, if we go back to that factorial problem, you can't get the factorial of even small numbers like, 2000 or 1001 because you'll cause a stack overflow. And the way you get rid of that is with tail call optimization, which is essentially just forgetting, it's removing things from the call stack, because it turns out your algorithm doesn't actually need that. So if we go back even further to like function A calls function B calls function C, and it keeps track of how to backtrack, from C to B and then from B to A. It keeps track of that with the call stack. For factorial, if it turns out if the last thing that your recursive function does is call itself and then return that result, you don't actually really need to backtrack to the previous calls of the recursive function, because there's nothing for it to do after the recursive function call. I realize this is going to be like kind of hard to imagine, but essentially, you can use tail call optimization when your recursive function doesn't actually need the call stack for anything. And remember, recursion is just using a loop and a stack, but tail recursion is a loop and a stack without the stack. So you should just use the loop. And
Yeah.
and I've looked at this, and again, it's one of those things where it's a clever hack to get your recursive function to work on real world computers and things like that. And so it makes people feel really smart to do this because it's a clever optimization, but it's an optimization that you don't really need it in the first place. So it's just more confusing and convoluted code. And I thought about it a long time, and I thought, yeah, you actually never need to use this. And it turns out, I think this is actually not a controversial statement, because Python, the Python interpreter, the CPython interpreter specifically, the one that you download from python.org, that does not implement tail call optimization. So even if you wrote your code in a way to do this, it really depends on the compiler or the interpreter detecting this and then applying this optimization behind the scenes to prevent stack overflows. And Python's interpreter doesn't do this at all. And Guido has written a couple blog posts about why this is. He says that it really interferes with the traceback messages that appear when you're debugging.
Yeah.
But I looked into this, and I think every major JavaScript interpreter also doesn't have this as an optimization. If you open up your browser's debugging tools and you just write a bit of JavaScript code where you have, just a function that calls itself, this shortest recursive function example, or rather you just write a factorial, recursive factorial function that also has tail call optimization, it's going to crash in a Stack Overflow because that JavaScript interpreter doesn't actually use this. And I think also the latest versions of the Java compiler also don't have tail call optimization. So like Python and JavaScript and Java purposefully don't implement this. And I kind of realized, like, yeah, it is sort of a sign that this is not actually a technique that you should use. Of course, in functional programming languages, where essentially you don't even have loops, you just use recursive function calls as your loop, tail call optimization is very much necessary in that. But also, I feel like this is a reason why nobody really likes to use functional programming languages, or rather why they're not as, they don't have that mainstream popularity, because it's actually something that's, it just makes your code more complicated, and there's easier ways to do it. So why not do it the easier way?
Yeah. When you were thinking about writing this book, were these some of the things that you were most excited to write about?
I mean, I originally thought that this would be a super short book. I approached No Starch Press with the idea originally of like, hey, what if we just did like a 70-page or 100-page book? It's really short.
Yeah.
Because, recursion, how much could I possibly talk about that? But, and then it just kind of grew into a regular sized book. And I started looking at all these sort of related concepts, like tail recursion and stack overflows and memoization. And that led me to dynamic programming, which I realized dynamic programming itself, it sounds very fancy. Apparently the name came about, I forget the name of the computer scientist, Bell, I think. But anyway, he basically wanted to get funding from the Department of Defense back in the 40s or 50s or whenever. But one of the administrators just really hated spending money on research, and what he wanted to do was essentially just programming research. And so instead he just said, well, it's dynamic programming, which is sort of a meaningless name.
Huh.
But and that's what it came from. And I always thought like, oh yeah, what exactly is dynamic programming? Because it's also one of these terms I kept hearing all the time, and it seemed to use recursive algorithms as part of it. And it took me a long time to finally boil it down to a really simple sentence that I could never find in any dynamic programming tutorial. And that it's, okay, so dynamic programming it's the set of programming problems where you want to use recursion, but also you want to use recursion to break your problem up into similar, smaller problems, but there's also a lot of overlap between these problems. And so Fibonacci is an example of this. If you want to find the 10th Fibonacci number, you have to find the 9th and 8th Fibonacci number. And to find the 9th Fibonacci number, you have to find the 8th and 7th Fibonacci number. Well, you're recalculating the 8th Fibonacci number multiple times. So there's overlap right there in your recursive algorithm. And the way around this is just using memoization. And so really, dynamic programming is just recursion and memoization, because you have these overlapping sub-problems. And I could never just find that sentence in any of these tutorials on dynamic programming. And so I thought like, oh, well, okay, yeah, it took a long time for me to figure this out. And it's like, oh, this thing is actually just this other simple concept. And that's why this book is something I've been working on for about 4 years.
Took you on several journeys, yeah.
Yeah, it's amazing how much effort it takes to simplify concepts and kind of show that, like, oh, it's really easy to give it an intimidating reputation that of this like mysterious, technical, advanced topic. Yeah, it does sort of boil down to much simpler things. I also found out this is another weird thing, and also why I say that a lot of programming is just people repeating the wrong advice that they heard from other people. You'll often hear about top-down recursion and bottom-up recursion, and I've realized that actually there's no such thing. These are misnomers. What people actually mean is top-down dynamic programming and bottom-up dynamic programming. The idea is, so the Fibonacci algorithm is an example of top-down, where you start with, hey, I want to find the 10th Fibonacci number. Well, now I have to break that up into smaller problems of the 9th and 8th Fibonacci numbers. You have to find those, and then you could break those up into smaller problems. And so that's sort of like the top-down approach. You start with the result that you want, and you go down to smaller and smaller problems until you've solved the base case, at which then you can sort of reconstruct the total complete solution. And bottom up, so a lot of, if you think about it, all recursion is top-down recursion. The whole idea of bottom-up dynamic programming is sort of the other half of dynamic programming problems, where you start with like the small cases And so this would sort of be like, well, let's just start with 1 and 1, the first two Fibonacci numbers. We add those together to get the next Fibonacci number 2. And so you start at the small cases and then build your way up. So this is really bottom-up dynamic programming. And there's another technique in bottom-up dynamic programming, which is called tabulation, which is sort of like another optimization to do this. But really, the point that I want to make is that there's no such thing as top-down recursion or bottom-up recursion, because all recursion is top-down. And whenever I actually started looking for examples of bottom-up recursion, people would show this sort of starting from the base cases and building up. But I noticed their actual code doesn't have any recursive function calls. There's no recursive function, so how can it be recursion? And then I had to look more. It's like, oh, they're actually just getting these terms mixed up. And nobody's really pointing out that this is a really common misconception that people are making. And I feel like there's so many of these, tiny misunderstandings when it comes to recursion. And that's why people think of it as such a difficult thing. It's not that it's a very, it's like arcane, super genius topic. It's just mostly that it's really poorly taught.
Yeah. Yeah, it's too funny. When you're writing the book and you were coming up with the examples, was it difficult doing the sort of context switching between the Python and the JavaScript? Did you find that difficult at all?
Not really. I also tried to really keep the code as simple as possible. Like there are times where, I can, and I feel like this is a common thing with a lot of my books. If there's a simple way to do it and a complicated, but, elegant way of doing it, I'm going to pick the simple way of doing it. Every programming language has variables, and every programming language has functions and arrays or lists. And so for the most part, all of these examples are sort of one-to-one. You can look at this line of code and its equivalent in Python or JavaScript is this line of code. I did have this one idea for a programming book that is sort of like a Rosetta Stone of Python and JavaScript, because those are two of the most popular programming languages out there. And so I figured like lots of people are learning how to program in Python as their first language. A lot of people are learning how to program in JavaScript as their first programming language. And it's really good to learn multiple programming languages because it's sort of like traveling abroad. You sort of realize that all the things that your home country and your home culture, the way things that you do it, isn't how other people do it. So you travel not really to learn about other countries, but to learn more about your own country.
Yeah.
And the same thing with programming languages. There's a lot of things that Python and JavaScript do that you sort of take for granted, but then you realize, oh, programming languages don't have to be designed that way. So that's kind of nice. But I really just stick to like the simple concepts. Mostly, I just didn't want to restrict the book's audience to people who know Python. So for any JavaScript programmers who are listening to the Real Python podcast and who don't know Python, this is also a book that has code examples for you.
Yeah, that's nice. Do you, not to spill the beans on anything, but do you have any projects that you're looking at working on next?
Oh man, I always have about like 5 or 6 book project ideas.
Okay.
So like this Rosetta Stone kind of book was one of them. I had an idea for, I might have talked about this on a previous show. A lot of times my friends will tell me like, yeah, Al, you've been talking about this idea for years now. And I eventually get done with them. It took me 4 years to do the recursion book, but I finally did get it done.
Yeah.
Like an idea of a programming book that teaches you programming and Python that doesn't really use words. It just uses illustrations in the way that an IKEA instruction manual or a Lego instruction manual can teach you how to build a thing.
All right.
And I have no idea how I can do this or convey all of these topics. But I kind of figured it would be nice because then you don't need to understand English in order to program it. It's instantly available.
Localization will be much easier.
That'd be great. And also I figured I'd learn a lot about how to teach concepts that way, but that might be a too esoteric. I am working right now also on a book that is just sort of a bunch of very gentle programming exercises. There's a lot of these websites like Hacker Rank, coder, whatever thing. And I feel like
Sure.
those are great if you really want to challenge yourself. But for people who are just starting out, I wanted to gather up like all the really, really basic examples. The one that I always mention is converting between Fahrenheit and Celsius.
Yeah.
This is sort of a function that every programmer has written at some point because it's a very common exercise. And I just wanted to gather up 42 of these exercises into a book that I'm publishing it as sort of a 99-cent ebook, but it'll also be freely available under a Creative Commons license on my inventwithpython.com website. And so that's a project that I'm wrapping up right now. But
oh, cool!
Just so many things. I've been neglecting PyAutoGUI, which is a Python module that can let your Python programs control the mouse and keyboard for doing automation. There's an entire field called RPA, Robotic Process Automation, which does not actually involve robots, or when they say robots, they mean more like bots. And the more I look into it, the more I realize, oh, it's just simple scripts that click on things and type things for you.
Nice.
Yeah, it is fun. Mostly it's just usually the project that I'm working on leads to other projects. And I had a lot of fun with the projects in this recursion book as well. The second part of the book is sort of more complete, substantial programs that do something. So there's one that generates a maze. There's another that can solve those 15 tile puzzles. They're usually like the 4x4 tiles, and then one tile is missing, so you can slide them around, and you want to slide them back into order. I don't think I've ever
either them being numbers or them being like a picture or something like that.
Yeah, I don't think I've ever actually solved them. But if you think about it, it's analogous to solving a maze in that where the blank tile is and the setup of the board is sort of your intersection, and the path that you can go down is, well, do you want to slide the tile left or right or up or down? And then that just leads to another intersection where you have to decide which tile you want to slide, and then you want to backtrack. If eventually you figure like, okay, this is not the way to solve this, you can backtrack to earlier intersections by undoing the slide. So if you slid it to the left, you can undo that by sliding it to the right, and so then that's like, oh, you can make a directed acyclic graph out of this, which means that you can write a recursive function to solve it. And so that was actually a lot of fun, and I came upon like some other issues that you have to like solve in order to write this. But yeah, the complete code in Python and JavaScript is in this book. And then there's also just a fractal art maker where you can use Python's turtle library, which allows you to just make these little line drawings and programmatically generated art. And I set it up so that you can just play around with some configurations, and you can take a basic triangle shape and then specify all these recursive call parameters to create just a huge variety of fractal images. And most of them just kind of look weird or nonsensical or just uninteresting, but some of them are pretty nice.
Yeah, fractals are fun.
Yeah. And then the very last project is there's a thing called the Drost effect. I'm not even sure if I
had never heard the name of it.
Yeah.
I thought that was cool.
Yeah, everybody knows it, but they don't know the name of it. It's if you've ever seen an illustration or a drawing that contains itself. And so the name comes from, I think, this Dutch hot chocolate powder, where the can that it came in featured a picture of this nurse holding a tray of hot chocolate and a can of the hot chocolate powder. And so on that can was also that same nurse holding a tray, including the can. And so it has the same recursive image. So using the Pillow, the Python image library, you can take any image and just draw magenta pixels over an area inside that image. And this program will then recursively keep filling in that magenta area with the image itself. But of course, that smaller image will have its own magenta area. And so it just recursively calls itself on that. So you can sort of create these interesting little like mirror into mirror kind of images with any photo that you have. And so I thought that was pretty nice. And it turned out there were like a few different issues I had to solve, but I came up with a Python program that can generate those fairly easily, and it's nice. And it's like, oh, okay, you just have to figure out all the hard parts, and then explain them. And I feel like it's a lot easier once you see the code in front of you. You can see like, oh, I understand how this is working now.
Yeah, I went and brought up that book. The little schemer book has one on it. Oh, actually.
Oh yeah.
The elephant is holding the book, and of course the book has the picture of the elephant with the going on and on.
Yeah, when it came to the cover design of this book, I also have that where it's a picture of a robot reading a book, and then of course the book is the book itself. So there's a robot on on that cover reading a book
right.
over and over again, and I felt like I can't not have that as the cover.
Yeah, I got to do
of this book.
That's funny.
Yeah, it's this book was pretty exhausting to write, but it's now done. It's coming out on Amazon in August, but you can actually get the early access ebook from No Starch, and I always recommend people buy the book from the publisher directly because you get those free ebooks as well. And I believe the early access ebook has all the content of the main book. I feel like just because it's not yet officially released, they still call it early access, but it's essentially the full book, and you'll also get the full book when that comes out as well if you buy the early access one.
Nice. Well, I think that takes us to the weekly questions I have.
Oh yeah, sure.
So, what's something that you're excited about in the world of Python since we last talked?
Wow. So, Textual is sort of a project that I've been following.
Yeah.
And
Will McGugan?
Yes, exactly. A lot of that work, and so. And just the term TUI for text user interface, as opposed to like GUI, the graphical user interface. And so, this is for applications that have windows and buttons and checkboxes and things like that. But in the before times, before we had, Windows and Macs, we all just had the command line. But we also, using text characters to draw lines, we could sort of create these very primitive looking graphical user interfaces that way. It's sort of like zip disks. I feel like there's like this brief moment where they did make a lot of sense.
Yeah,
between like small floppy disks and then burnable CDs, but then they were quickly sort of like forced out and no longer used. But TUIs are a thing, and maybe it's just because I'm old and nostalgic, but I do like the simplicity of them, and they do offer sort of, even though they look very basic. It's a lot easier to program and deal with them, which is great if you just have very simple programming tools that you're creating for yourself or for a few others, and instead of a fully polished product. It's sort of like how Minecraft has that very retro aesthetic, but at the same time, it's really easy to build things in Minecraft because there's just discrete blocks that you play with. It's not like a full CAD tool or some 3D modeling program like Blender that you have to learn, and that's really intimidating. It's really easy just to play around with blocks, and I feel like the same way with the textual module.
That's funny.
Yeah, I've only dived in a little bit into like the Hello World examples of it, but I'm really excited to get more involved in that, and also just the Beware project for putting Python on mobile devices.
Yeah,
it's something that I've been looking at for quite a while now.
Cool.
Yeah,
and what your conversation about that, or your talk about that, made me think about is just the idea of creative restraints. There's so many, or constraints.
Yes.
Having constraints is always kind of nice in the sense that when there's a million possibilities of a way of doing something, you just sort of can have that sort of overwhelming amount of choices. And it's nice to say, let's just learn how to do it this way.
Yeah.
and dive into it, which is really slick.
Yeah, so it really cuts down on just the possibilities that can really paralyze you.
Yeah, definitely. Get something done.
Yeah. And so we actually met up at PyCon this year, and I think the big news from that was Python in the browser.
Yeah.
Which I feel like a lot of people are also very excited about. The presenters did stress like this is sort of an alpha release or something, but I'm also excited about the idea of Python running in the browser.
Yeah, definitely. I'm keep playing with it a little bit. I'm actually thinking about talking with Russell from Beware, because he's kind of indirectly connected in some ways. he got funding through
Anaconda. Yeah. Russell
Anaconda
Keith
is helping
McGee.
him as his project. Yeah. And so I'd like to kind of hear a little bit about that, because last time I talked to him was over 2 years ago now, about just kind of where Beware was, and the, kind of looking for help and so forth. And so
Yeah.
I'm glad to hear that, he's got some funding to kind of keep working on the project, but also that there's some nice tools that can kind of be generated. There's, this idea of, writing Python once and deploying everywhere is definitely, the web is part of that. So that's great.
Yeah. I mean, Python is such a great language, and an accessible language, that I really want to see it being used in more and more domains. And sort of like the browser and mobile devices are two areas that Python hasn't conquered yet. So I'm definitely excited about any gains that Python can make there.
Yeah, definitely. Cool. So what's something that you want to learn next? This doesn't have to be Python or even programming related.
Oh man, it's always programming related.
Okay.
Well, so this is partially programming related. There's an idea that I've been kicking around my head for a while. One talk I saw at PyCon this year actually renewed my interest in it. But what one of my friends pointed out to me is that all of my hobbies have something in common, and that's that they're all really cheap. So like writing software is something that like, you can just use a free Python tool and like the laptop that I already have. And going for walks or like playing Pokemon Go or something, like, yeah, that's all free and cheap. You don't have to like fly out anywhere, or you don't have to buy like
Yeah.
a lathe or
Yeah.
expensive equipment and materials and things like that. But one of my cheap hobbies is origami.
Oh, okay.
And it's great to just follow along with YouTube videos and learn some other folds like that, because when I was a kid there was just origami books, and
Yeah.
there would always be a part where I follow the diagrams, and I get stuck at one point and I don't have a fox or a crane or
Right.
whatever. I just have a mishmash of folds or something like that. So the videos are kind of nice because you can actually see the entire process.
Yeah.
But one bad thing about the videos is that, there's always these like big meaty hands in the way of it, or they'll like move a little too fast on some parts. So I thought it'd be great if I could use sort of like cloth simulation algorithms, except instead of cloth, just makes it much more rigid like paper, and then simulate folds on that. And then so it's essentially like, I want to write this software where you can simulate folds and record the movement of the paper as you fold it. So there's lots of other issues that come up with this, but then you could play it back and view it from any angle, and essentially have these instructive, interactive websites or applications that show you how to fold all of these different things. I always thought that was great. There was this one talk at PyCon that went into Blender, the 3D modeling software, and having all these like constraint satisfaction problems, which is sort of related to what I want to do here. And I thought like, oh, hey, I should start looking into how to do all of this again. So this sort of like origami folding idea.
Yeah, that sounds really fun.
Yeah, it's probably an idea I had.
And any particular channels on YouTube you want to share?
There's a bunch of them. I think Joe Nakashima. Hopefully, I got that name right. But generally, if you'll just search for origami and tutorial or something on YouTube or any video site, there's a lot of great people who have just pretty simple folds. Generally, I feel like any origami model that you're trying to fold, that's, if the video is longer than 20 minutes, it might be a bit too much. But anywhere from like 0 to 20 minutes. And usually I'll set aside an hour when I'm first learning it, because I'm constantly pausing the video and rewinding a little bit just to watch it.
Yeah, I bet.
Yeah.
This scorpion one I'm looking at right now.
Oh yeah. Yeah, it's one of those things where I guess it's sort of the opposite of computer programming, because learning all these cool programming things, especially if you want to do like machine learning or AI, and it requires like massive data centers to just crunch through all these numbers, that's something that we can only do here in the 21st century. But with origami, it feels like there's something nice that I could go back 1,000 years, and all I need is a square sheet of paper, and I could recreate the most complicated origami models if I just knew how to fold it. It's something that doesn't really require like technology, just knowledge and a little bit of insight. And
Yeah.
there's something I really like about that. Also, paper is cheap.
Yeah.
So those are the types of hobbies that I generally like.
That's cool. So what's the best way that people can follow the things that you do online?
So my website is inventwithpython.com. It's where I publish all of my Python programming books, and they're all freely available under a Creative Commons license. So you can read the entire book for free online. There's also links to the publisher's site, where if you want to buy a nice print book or a much better formatted ebook, you can buy it there. And from there, I have links to sort of the occasional YouTube video that I'll create, or online courses that I've also created. But inventwithpython.com is sort of where people can find me online.
That's great. Well, Al, thanks so much for coming on the show again. This has been a lot of fun.
Yeah, thanks for having me. This is a kind of a hard concept to relate just in the audio only format, but hopefully, I've at least sparked an interest for people to learn more.
Yeah,
and not be scared off as well.
You definitely answered some more of my questions, so that's great.
Thanks a lot. Yeah, thank you.
I want to thank Al Sweigart for coming on the show again. And I want to thank you for listening to the Real Python podcast. Make sure that you click that follow button in your podcast player. And if you see a subscribe button somewhere, remember that the Real Python podcast is free. If you like the show, please leave us a review. You can find show notes with links to all the topics we spoke about inside your podcast player or at realpython.com/podcast. And while you're there, you can leave us a question or a topic idea. I've been your host, Christopher Bailey, and I look forward to talking to you soon.